Hello everyone, it's me again, back with another video. For today, we will be discussing about Kruskal's algorithm. So Kruskal's algorithm is another way for us to get the minimum cost spanning tree, or the MST. And prior to this one, we discussed about prims, but a lot of you were able to understand prims. And by popular demand, you guys said, "Sir, Kruskal's is something that we couldn't fully understand. It's quite difficult. So let's just try to get through this together, okay?" So we'll start first with how prims works. So if you can recall with prims, we initialize the set U to contain the first vertex that you are going to use. And while U does not contain all of the vertices in V, we find the minimum cost edge UV such that U is in U and V is in V minus U. So if you can recall, you start with your set U, or your first vertex. We look for an edge from U and V minus U. So V minus U is 1, 2, 3, 4, 5, and we're looking for an edge from 0. So in this case, if we look at this graph, we know that there are how many edges here? That's 1, 2, 3, 4, 5 to check. The smallest one is 1, so that's what we add to our U. We do this again, but for this time, we are going to check for any edge from 0 to 2, 0 to 3, 0 to 4, 0 to 5, 1 to 2, 1 to 3, 1 to 4, 1 to 5, because we're looking for the minimum cost edge UV such that U is in U and V is in V minus U. So we are going to look for that. So far from 0 to 2, 3, 4, 5, the smallest one is 4. That's possibly it. So let's look at the edges from 1 to 2. That's 5. 1 to 0 is 1, but we already have that, so we can't use. 1 to 5 is 6. So far the smallest edge is this one, from 0 to 3. So we add that vertex into U. 3 was added. We do this again. We find the minimum cost edge UV such that U is in U. So in this case, we're looking for an edge coming from any vertex in U. So 0, 1, 3. And we're looking for any edge from 0 to 2, 0 to 4, 0 to 5, 1 to 2, 1 to 4, 1 to 5, 3 to 2, 3 to 4, and 3 to 5. So from 0 to 2 is 5, 0 to 4 is 6, 0 to 5 is 5. So currently the smallest one is 0 to 2 and 0 to 5. Let's look at 1 to 2. 1 to 2 is also 5. 1 to 4 doesn't have a direct edge. 1 to 5 is 6. So far 5 is still the smallest. And let's try with 3. 3 to 2 is 2. So this is now currently the smallest. 3 to 4 is 1. Oh, now this is the smallest edge now. 3 to 5, there is no direct edge, so that doesn't count. So we know that this is the smallest edge from 3 to 4. So we add V to U. V meaning 4. So you'll notice 4 was added. Then we do it all over again. Find the minimum cost edge such that U is in U and V is in V minus U. So now we're checking for 0 to 2, 0 to 5, 1 to 2, 1 to 5, 3 to 2, 3 to 5, 4 to 2, and 4 to 5. 0 to 2 is 5, 0 to 5 is 5. 1 to 2 is 5, 1 to 5 is 6. 3 to 2 is 2. This looks like the current smallest one so far. 3 to 5 doesn't exist. Let's look for 4 to 2. That doesn't exist as well. And 4 to 5 is 3. So currently, the thing that's currently smallest is 3 to 2 because it has a weight of 2. So we add vertex 2 into my U. So I added that into my U. Now take note, every time we added a new edge, we're also adding the cost of that edge to our min cost because we are trying to create the minimum spanning tree. So you'll notice 1 plus 1 plus 4 plus 2, that's equal to 8. 6 plus 2 is 8. Now for the final iteration, we are going to do it all over again. And always take note, we're always checking if u is not yet equal to v. And you'll notice there's still one more vertex that wasn't added into u, which is 5. So now we just need to find an edge that connects 0 to 5, 1 to 5, 3 to 5, 4 to 5, or 2 to 5. So let's look for that. And it has to be the minimum cost edge. So from 0 to 5 is 5. That will be our current smallest. From 1 to 5 is 6. That's not smaller than 5. 3 to 5 doesn't exist. 4 to 5 is 3. That's our new smallest. And then 2 to 5 doesn't exist. So we know that this is the edge that we need to add. So add v to u. V is 5. So I'll add that to u. So you'll notice it's been added to u. The while loop will check for while u is not equal to v, and you'll notice u and v are already equal. They both have the same number of vertices or elements. So my loop will stop. And I was able to get a min cost of 11, and I was able to generate my minimum spanning tree. That's a very simple algorithm for prims. Now Kruskal's is a bit different. So for Kruskal's, we initialize a graph T containing vertices but no edges. So we have all of the vertices in the graph, but consider that they are not connected with each other. And take note, graph G is different from graph P. Graph G is the input graph, and graph P is our output graph. Each graph or each vertex is connected component by itself. What is a component? Let's just think of it as a group of vertices. So while all the vertices are not yet in one component, meaning while all of the vertices are not yet connected, we are going to find an edge uv with a minimum cost that will connect to vertices in two different components. So what are we trying to do? We are trying to connect two different vertices that do not belong in the same component. Okay? So let's start. We start by initializing graph T with all of the vertices but no edges. This is what it looks like right now. Next, we are going to look at the graph and we are going to find an edge with a minimum cost. So in this edge, you will notice that we have weights. Which of these edges have the smallest cost? We have these edges with 1. So we can use 0, 1 or 4 and 3. Let's just use 0, 1. So if we found the edge that we want to add, we just need to add 0 and 1. So they are now connected. We are going to do that again. In this graph, what is the next smallest edge? That's from 3 to 4 or 4 to 3 or whatever. So we are going to connect them. Next, we are going to look for the next smallest edge. 2 to 3 looks like the smallest edge. That's 2. So we're going to connect them as well. Next smallest edge is 4 to 5. And that's the weight of 3. So we'll connect them next. And finally, we need to look for an edge. Take note, we need to look for an edge that connects vertices of two different components. What does that mean? If I have an edge, if my smallest edge is, let's say, from 5 to 3, assuming that exists, it isn't technically it's not connecting two different components because 5 and 3 are already in the same component or group. So we're looking for an edge that comes from this specific component, C1 and 0, to this specific component. Okay? So in this case, the smallest edge that I can find that connects the two components is 0 to 3, which has a size of 4. So we are going to add that. Is the graph already one component? You'll notice all of the vertices are connected already. So the graph is one component already. So therefore, the final result of Kruskal's is the exact same graph as that of Prim's with the same minimum cost. So look at Prim's, that's the result. This is the result of Kruskal's. So it's the same. Now I think the thing that the students have a problem with is, how do we determine whether or not I am still one component? And that's what I am going to discuss to you guys right now. So if we go to my trusty kanang whiteboard here, let's recall the concept of parent pointer implementation. You could think of this drawing as a tree, but technically you're right, because this is a tree. But if you were to think about it, technically all trees are graphs. So we can still use the same concept with trees for graphs. Or we could also do the other way around. But the point here is, I have a tree, and if you can recall parent pointer implementation, what we do is we let the index reference the specific vertex, and the value inside the index is its parent. So who is the parent of 0? 0 does not have a parent, so the value is -1. Who is the parent of 1? It's 0. Who is the parent of 2? It's also 0. Who is the parent of 3? 0. The parent of 4 is index 1. The parent of 5 is index 2. The parent of 6 is index 2. The parent of 7 is index 3. This is the parent pointer representation or implementation of my specific tree. Now we can use the same concept to determine whether or not all of the elements are connected. In this specific case, the drawing tells us that everything is connected. Would you believe me also if this specific drawing also tells us that everything is connected? Yes, we can. We can just go by going per parent. So, for example, how do I know if 7 is connected to the graph? I can just go to its parent. 7, the parent of 7 is 3. So I'll go to 3. The parent of 3 is 0. 0. The parent of 0 is -1. So he's the root of the tree. 6. The parent of 6 is 2. 2. The parent of 2 is 0. And 0 is the parent of everything. So you can go through each of the elements, and you will somehow end up merging or being able to represent this specific drawing in the parent pointer implementation. We can do the same concept with our graphs. So I drew the graph here. I drew a sample graph here, and we have our representation here. So let me just close this so we won't have difficulty. I have an example of a graph representation here, and we'll try to do Kruskal's with this graph. So the first step in Kruskal's is we are going to create a new graph T. So this is graph G. Graph T will look like this, a graph with no edges. So what we're going to do is we're going to start by determining, and that wasn't part of the presentation, but the efficient way of doing this is you are going to get all of the edges, and then you are going to sort them. So you will know which of the edges are smaller. So take a look at what we're doing here. We have all of the edges, an edge from 0 to 2, an edge from 0 to 3, 1 to 2, and so on. So all of the edges in this graph are represented here. These edges are currently unsorted, and in the minimum cost spanning tree, we want assorted. We want it sorted in ascending order because we only care about the smallest values in our tree or in our graph. So you'll take a look. If I take the step forward, we sorted all of the edges together. But before we continue, I want you to take note of this disjoint set. This disjoint set represents the same parent pointer representation that I am showing here, except it's a bit different. Let's take a look at how it looks. So let's start now. Now that I know that this specific edge, before we continue, let's take a look at the disjoint set. It just says that the parent of each vertex is -1. And since we are working with graphs, I don't want to use the term parent because I guess it doesn't really make sense to me. I like to use the term representative. So what does it mean? When there are two groups of, let's say, vertices, let's say, for example, going back here, let's say 1, 0, and 3 are connected. This is one group. In this one group, we are trying to get a representative, or somebody that would represent the connection between all three of them. It can be anyone, but we need to make sure that it's consistent. Let's just show you how it works in the algorithm itself. And if you tried to look into this, you need to start looking into what a disjoint set is, or it's called the union find algorithm. So because all of these different vertices are not yet connected, technically, their parents or the representatives are still -1, meaning they represent themselves. Okay, so I had to cut for a while. Important stuff happening in the background. I forgot what I said prior to that cut, but anyways, just remember that the disjoint set represents our parent pointer implementation. So since all of these vertices are not yet connected, they will have -1 as their parent. Meaning, they don't have a parent, they're on their own. I think for this, let's just say they don't have a group yet. Let's call it group, not parent for now. So currently, they are all individual groupings or individual components. So there are currently 8 components actually. 4, 8. There are 8 components. So we were able to group all of these, we were able to sort in ascending order all of the edges. So we'll start by looking from 0 and 2. So we'll look at 0 and 2. We're going to basically look for the parent of 0 or the representative of 0, and we're going to look for the representative of 2. So let's start with 0. Who is the representative of 0? -1. Meaning, it represents itself. It is its own group. So that's good. Next, we look for the representative of 2. The representative of 2 is also -1. Meaning, it represents itself. It's its own component or its own group. So, that's also good. Meaning, if they don't have representatives or if they don't have their own group, then they can group together. So in this case, they'll try to compare with each other. Which of these vertices have a bigger group? 0 or 2? Technically, they have the same groupings or number of people in their group. They are both a group of 1. So it doesn't matter which of the two vertices you will consider as the representative, but it's always the one with the bigger group. The one with the bigger group. So for example, if I had groupings like this, example lang, 0, 1, 3 are a group, and let's say 2 and 4 are a group. When we merge both of these different groupings together or group of components together, the leader of the group must be this specific group, whoever the leader of this group is, because this group is bigger than this group. For now, just trust the process and we'll understand better. So right now, our two groups are 0 and I mean 0 and 2. Both of them have the same size, so it doesn't mean, or same number of vertices, or same number of vertices, same number of group mates. I don't know what term you want to use, but let's just call them group mates. They all have just one group mate themselves. So we want to merge them together. And we will choose which of these two will be the representative. It doesn't matter because they are the same. So in this case, we chose 2 to be the representative. Because you'll notice 0 is now under 2. Or the parent or the representative of 0 is 2. The representative of 2 is now negative 2. Meaning, I added negative 1 to negative 2. We'll look at that later. So what that means is I grouped 0 and 2 together. Okay, I grouped both of them together. And it just so happens that the leader of this group, let's just call this, the leader of this group is 2. Let's move on to the next. We now have 2 and 6. Or we're looking for the next smallest edge, 2 and 6. The edge from 2 to 6 is the next smallest edge. So what do we do first? We want to look for the representative of 2 and the representative of 6. The representative of 2 is itself. The representative of 6 is also itself. But if you take a look here, we are trying to connect 2 and 6, right? 2 and 6. They are two separate groups or two separate components. Therefore, we can connect them together. So essentially, what we want to do is we want to connect 2 and 6. But which of them is the bigger group? The bigger group is the group of 2. The group of 2 is bigger. Therefore, 6 will join group of 2. So if we delete this, we will now have this, and then we are now going to group this together. What does that look here? What this looks like is, because 6 is going to be joining 2, we are going to add negative 1 to negative 2, and we are going to say that 6 is now represented by 2. So take a look at what happens. Because they are in different trees, we are going to move negative 1 and add that to negative 2. And we are saying now that 6 is now under group 2. 6 is now under group 2. Now, what does this negative 3 represent? This negative 3 is technically the number of vertices that are inside your group. So take a look. In the group 0, 2, and 6, in the group 0, 2, and 6, or let's just call it group 2, because 2 is the leader or representative of this group, there are 3 vertices. It's important to know which of these. This is important because we always want to connect to the bigger group. So let's keep going. Next, we are going to look for 5 and 7. So if you can recall the steps, we're going to look for the representative of 5 and the representative of 7. So the representative of 5 is negative 1, meaning wala siya kagrupo. So let's draw that here. 5 does not have a group mate, so he represents himself. 7 does not have a group mate as well, so 7 represents themselves as well. So you'll notice 5 is negative 1, 7 is negative 1. So meaning because they are of different components, we can merge them together as one group. So we are now going to have someone be the representative. So in this case, for this specific example, we are letting 7 be the representative. So I think if you want to be consistent, if ever they are of the same, if they have the same number of members in their group, maybe you always have the second vertex be the representative. So in this case, si 5 mo ini give way, you'll notice 5 will now be represented by 7. So in the drawing, what will that look like? 5 is now like this. This is now what I will call group 7. So let's keep continuing. We are looking for 1 and 2. Okay? So we're going to look for the representatives of 1 and 2. 1 is represented by himself. Wala siya'y friends. So let's consider this a new group. That's 1. 2, let's look for the representative of 2. So you'll look at 2 and you'll notice it's negative 3. So he says 2 is a representative of itself, and in his group there are 3 elements. So we are now comparing this group, C1, and this group, which is group 2. Group 2 is bigger than group 1. Group 2 is bigger than group 1. So that means si group 1 ang akong isulod ni group 2. So what does that look like? Negative 1 will be added to negative 3, and 1 will be represented by 2. So take a look at what happens. So now 1 is represented by 2. So take a look. I'm now going to add an arrow going from this to this. And now this is my new grouping. So we are going to keep doing this until all of the vertices are under one group. So let's keep going. 2 and 5. So 2 represents itself, and he has 4 people in his group, or 4 vertices. 5, if we check 5, he says 5 is being represented by 7. So Murshag, take me to your leader, talk to my leader before we merge. So let's look at 7. 7 represents his own group. 7 represents a group of 2 vertices. So if you look here, you'll see group 7 and group 2. Which group is stronger or has more elements? See, group 2. Therefore, what do? I am going to merge group 7 and group 2. So since group 2 has more vertices, I'm going to move negative 2 and add it to negative 4, and then let 7 be represented by 2. So you'll notice that there, and you'll notice 7 is now represented by 2 as well. So in our drawing, that would look something like this. So I'm going to erase this grouping. Gi-absorb na si 7 og si 2. So 7 is now under 2. And we are going to erase 7 because it now belongs to group 2. So let's look at the next example. We have 3 and 7. So 3 represents itself. So if we look at the drawing, 3 represents itself, a solo groupmate. We're going to look for who represents number 7. So we're looking, 7 is represented by 2. So let's talk to my boss. My boss is number 2. So we go to number 2. We say, wait, 2 is negative 6. 2 is a boss of a group of 6. A group of 6 vertices. So I stop. I'm the boss. We can now talk about merging. So 3, vertex 3 is a group of 1. Vertex 2 is a group of 6 vertices. So the bigger number of vertices win. So that means 3 will be merged with 2. Or group 3 will be merged with group 2. So negative 1 will be added to negative 6, and 3 will be represented by 2. Next is 3 and 5. So let's look at 3. 3 is represented by 2. So ni-add to tani 2, talk to 2. 5 is being represented by 7, which is also being represented by 2. So meaning, if we look at 3 and 5, for a moment, let me just bring 3 to the group. 3 was represented by 2, so that means 3 is now pointing here. This is the entire group 2 now. Dako na kay si group 2. So in this scenario, you will notice Our edges to connect, or vertices to connect, are 3 and 5. So remember, we're going to look for the representative of 3 and 5. So we're looking for the representative of 3. So si 3, kita siya 2. My boss is number 2. Please talk to number 2. 2 is a boss. 2 is the boss. He is a representative of 7 vertices. Let's look for the boss of 5. 5 is being represented by number 7. Number 7 is being represented by number 2. And 2 represents a group of -7. So if we take a look at this drawing, we were trying to connect 3 and 7. And then, makarealize sila nga, hala, pariha raman na ita grupo. Di naman siguro ta kailangan mag-connect kay si Tura maghihapon ng atong mafia boss. So, yeah, that's it. Because they are already connected, there's no point in connecting them together. So, you'll notice vertices are in the same tree, so we skip the edge. So, we are going to look for the next edge. 2 and 4. 2 is represented by himself. He's a leader of 7 vertices. And 4 represents himself, a lone wolf here. Solo group siya, si 4. And then we check again who is the bigger group. It turns out group 2 is bigger, so we're gonna merge them together. -1 is added to -7, and 4 is now represented by 2. So if I delete this, 4 is now represented by 2, and now I now have 1 component. So at the end of the day, all of the vertices were connected under group 2. Amazing. If we want to visualize this differently, and if you want to visualize it like a tree, you can also visualize it like a tree. You can say 2 is the parent of 0, 1, 3, 7, 6, 4. 0, 1, 3, 6, 7, and 4. And 7 is the parent of 5. So this is my resulting minimum cost spanning tree. So if you take a look at the drawing as well here on my thing, 2 is connected to 0, 4, 6, 7, 0, 1, 4, 6, 5, 7, and 3. So muna siya, guys. This is my minimum cost spanning tree, and I knew when to stop because all of the components are in one group. I hope this gives you more insight as to how to code Kruskals, how to know if there is a cycle, because you'll notice my end result. If you take a look at the result here, there is no cycle here. It's a minimum spanning tree. It's a free tree. So basically, to summarize, the steps for Kruskals. The step for Kruskals is create all of the edges first. After you get the edges, sort them in ascending order. For each of the edges, look for the representative. Once you find the representative, and if they are not represented by the same vertex or they don't have the same representative, merge them together based on which one has more people in their group. If the number of people in the group are the same, like for example 0 and 2, let's just say that the second vertex will be the representative or the parent. So you'll notice 0 and 2 became the representative, so 0 is represented by 2. 2 is now a leader of 2 vertices, or a leader of a group of 2 vertices. And we'll just keep doing that, and so on and so forth, until we end up with this specific tree. Okay, So I hope you guys understand. I hope this makes Kruskal's a lot easier to implement, and good luck with your exams, guys. I'm rooting for you all. Bye!